actually discuss about mu bar in femboy theory. So this mu bar, it takes our topological space O cross P, or our state space, our femboy space O cross P, and takes it to P. Or if we think in terms of F, then mu bar maps F itself onto onto our P here. And P here is an interval. P is in fact an interval, so it's a subset of R. And can in fact be between 0 and 1. So P can be the interval. Can be the interval 0, 1, or P can be the interval 0 to 100%. We're just expressing things in terms of decimals, and then is in terms of percentages. So 100% is equal to 1. 50% is equal to 0.5. 1%, you guys can see it, 1% is equal to 0.01. Yeah. So it takes a femboy and associates it with a value inside P. So mu takes a femboy F, one femboy inside our femboy space, or our universal femboy set. Now this time we're expressing F in terms of and then associates it with us a value alpha, which is an element of P. Now F here is a two-dimensional plane, so just gonna sketch it real quick. But we must note that it is only in one extreme, which is the if we think of one plane as like this as, of course, this is the male and female axis, which is our presentation P, and then our orientation. We'll notice that, right, of course, the entire space here, the entire space is O cross P. O cross P is the entire space. The entire thing, it's a two-dimensional manifold. I suppose we'll also employ the Euclidean metric. Also, of course, it's this equipped with its topology, of course. So we have a topological space, which has a notion of continuity, because any curve that we create here, say a curve like that, or like this, if we make any curve in it, orientable curve, of course, then these guys are smooth until we break them. Of course, this one's not smooth anymore. This isn't a smooth curve anymore. Well, this is still a smooth curve. So this curve is a C infinity, and this one's not really C infinity. Now, okay, so this is the entire O cross P. But the thing is, when we're talking about mu bar in terms of femboy theory, we want to just think about the portion of this entire space wherein the person identifies as female. So we're only considering males here, okay? So like maybe assigned male at birth people, we're only considering those guys. So what we want to do, because we're only dealing with femboys in this theory, we're not really talking about very masculine guys or something like that. What we want to do is take half of this away. I did mention this, I did discuss this well in previous videos or previous lectures, but what I want to do is take away this half of the entire space. But of course, we want to maintain the orientation, of course, like guys or like girls or something like that. So we want to maintain this. So this is O, P. Now of course, if we express P as some union between two intervals, namely minus infinity to, oh of course not included, because you can include infinity, to 0. The 0 here is just our 0 element, or the origin here, and then take the union that with 0 again, and then to positive infinity. I'm not gonna put the positive sign here anymore. We just imply that if it's like this, it's positive, and we imply a negative infinity if we put a negative in front. If it's not, then immediately it's positive. Okay, so what we want to do is take away this branch. So our new f space, which we always work with from here on out and other lectures here. I actually don't know where to put this footnote, but I'll just put it wherever it's necessary, where I think it's necessary. So this f is basically just now, since of course we're only dealing with everything here. Okay, so let's suppose in this theory, in our theory, that this part of the axis. So I'll draw it here. Let's suppose that this part of the axis, or this part of the space, deals with the feminine trait. So it's all f here, and then this part here, this extreme here, is all male. So we're going to say this is m, this is f, or let's say that this is m and this is f. M is simply just p minus, and f is p plus. It's like integers. Z plus is just all numbers minus infinity to 0, such that all a, z here is all a inside the interval minus infinity to 0, such that a is a whole number. And likewise with z minus is just a as part of the reverse interval. So it's this time 0 is included, or 0 is at the left, and then we have positive infinity, and then a. Oh, yeah, we get it. So so like this, we're expressing using the notation here to denote two extremes. So yeah, let's use that notation. So let's use that notation. Okay, so let's use that notation in expressing f here. And so f this time now is so we want to take this away. So we want to erase all that, and all the space that we're dealing with is only this entire thing here. There's nothing here. Think that there's nothing here. And so that would just be f is equal to p, mathcal p, set minus the interval minus infinity to 0. Or it's just the same as p set minus p minus, or m, or that's equal to p minus m. So that's our f interval. And again, this is a two-dimensional space, so every femboy here is represented with two coordinates, or with two attributes. So every femboy, every f in f is a vector containing two components. Or it could just be a regular element that's or ordered pair. So in the most general sense, okay, let's use the most general sense. So the most general sense tells us that f is an ordered set, or ordered pair. It's an ordered pair. Which I will use angle bracket notation. Let's call it fx So every femboy in our femboy space is a ordered pair. Yeah, it's an ordered pair. Such that f of x, or f sub x, is part of the p interval, or rather, our new interval. So this now, of course, we maintain, we don't care about whether the femboy is straight or not, because it's an inclusive principle that femboys can either be straight or gay. So it doesn't matter whether we want to take away something. It really depends on you, but for us here in our class, we're just gonna maintain it and keep it like that. So although if we take this region away and just confine it to gay femboys, we would still get a two-dimensional space, and every femboy would still be represented as a two-dimensional ordered pair, or ordered pair of rank 2. But what we want to mainly focus on is really we also want to consider negative parts here, or the additive inverses of these parts here. So I don't want to say negative inverse, or I don't want to say negative because that implies that we are describing not straight femboys, not gay femboys, as negative or bad. So I would rather prefer to call it an additive inverse. So all these are all of the ordered pairs in this region are additive inverses of all femboys in this region. So a gay femboy over here cancels out directly with his straight counterpart here in this part. Okay, so let me just complete the syntax for this sentence and say this is p set minus p minus. So every femboy in F is an ordered pair, such that, well, the component here is part of that, and Fy and Fy is an element of the interval p. Oh, sorry. It's the y component, so it's in this part. So it exists in this part, or in this interval, this region. So O. Let's make it more. Let's use a different look for the O. There. So we're able to differentiate between O and 0, because sometimes you think that, oh, maybe this is a 0, or maybe this is an O. Just like how sometimes we can. That's why sometimes I use phi or var phi to denote phi instead of the usual phi like that. Sorry. Because if I use this phi over here, it looks like the empty set, because the empty set looks like this. This is the empty set, var nothing in LaTeX. But this psi here, regular psi, the psi that you know and love, the lowercase version of this psi. I'm sorry, no, phi, sorry, phi. Psi is this. Yeah, but the point is, what we want to do is make the notation as unambiguous as possible. So what does mu bar do to our system? So if we think now in terms of, if we think of our output space P, regular P, not mathcal P, because mathcal P here is our appearance interval. Well, what if we think of P now as a two-dimensional, another output space? So every femboy is associated with two attributes. So I guess their measure of gayness and some other property. So what this basically is a one-dimensional matrix. So there are many ways of describing. There's many ways of describing mu bar here. There's many ways of constructing the function for mu bar. Now, the conventional way that we constructed it back in femboy theory, femboyology, is that mu bar is equal to a piecewise function. And this piecewise function is, if I remember correctly, okay, so recall our O interval. O, and then this is our origin, O, O. This is our origin. Note that this part here, let's say that this region here, or this interval here, gives us a straight. So the inclinations for female, and then here the inclinations male. Okay. Okay, so this tells us now that if the O component of our femboy is, suppose that O is, so the person is 100% or full gay when their O component lies within the interval or lies somewhere. So they're 100% gay if, of course, their inclination is somewhere in infinity in M. So I suppose we can define an arbitrary threshold A, and then or minus A and positive A. We can define this threshold to be wherein it is halfway there, right? We can also restrict the entire interval to be just one thing. So this entire interval can run from 0 to 1. And of course, this is actually the best way to describe it. So this is now half. Okay, so oh, it's minus 1/2. Sorry. Okay, so this is 100% for O, which is for any O component of any femboy. That is at minus 1. And then 50%. 50% gay if O is I'm gonna write it like this. There. So the 0 and then O is different. Okay, so O 50% if O is minus 1/2. And this is practically the last component, but it'd be best if I define more components to this piecewise function. And so this now would be 0% or a null homosexual if O is equal to of course 0. So O is greater is greater than or equal to 0. And actually that's where we can end the piecewise function. And so this is u bar of O. Okay. Now notice that when we do graph this, it gives us a sort of probability amplitude. So when we graph it, so let's go a bit into probability statistics. So this here, let's suppose now that this over here is our scale from 0 to 1, 0 to minus 1. Of course, for our O interval. Now we can think of this as a Y component. So we get a distribution. So it's 100%. Of course, this is a discrete distribution. So at 1/2 or 1. So let's extend this a bit, but it's still at 1. So it only stays at 1. Okay. Let's just extend it a bit so that we have for blocks. Okay. So like this. Oh, sorry. Let's make that smaller. Okay. So if it's 0 or if it's at the origin, this is nothing. So its probability amplitude at 0 is nothing, or the output's nothing. Nothing, so nothing. And then at 1/2, we have something that's like this. And then at 1, we have something that's twice its size, so I'm going to estimate it. And then this, of course, is 50%. And then this is 2 times 50%, which is 100%. So now, if you think of Uber as a continuous function now, if we think of Uber as continuous, we get something like a wave function. So in terms of quantum mechanics, this now becomes So we're delving a little bit into quantum mechanics, and we noticed that when we start to think of mu bar as like literally just a probability amplitude, then we get the wave function, or at least the norm of the norm of the square of the, or the square of the norm of the wave function. So we already have, so now we're talking in terms of psi. And psi now is our probability amplitude. So we can define psi to be mu bar. In fact, this is another conjecture. So the conjecture is that psi here is our wave function. Or actually, no, let's name it a theorem, and then we'll prove it. So this is theorem. U bar is a wave function. Or rather, is the norm of a wave function. Is the norm of a wave function. Which I will call capital psi. How do we prove this? So the proof. Wave function. Let me rephrase the theorem. Is the square of a wave function. Psi. The wave function, or the square of the wave function, so the square of the wave function, I'll just write it here. So the norm of the wave function squared is a probability amplitude. Mu bar is a probability amplitude. And that's shown by our thing a while ago, so I'll just end the proof there with how it moves. So the theorem states that mu bar is the square of a wave function, which is a probability amplitude. And so this here is a probability amplitude. So the square of the norm of a wave function is a probability amplitude. So this is an important fact here, that mu bar, so an important fact, or this is an important formula, mu bar is precisely the square of a wave function, which is just the wave function times its complex conjugate. Because the wave function is a complex valued function, and taking its conjugate with itself gives a real valued answer, which is our probability amplitude, or real valued outputs, which is our probability amplitude. Thanks a lot to the post-nut clarity. I'm able to give a concise lecture. Okay. So this is an important fact here. And now, of course, I can just say that mu bar is, itself a wave function. I could have started with wave function, or with just the wave function itself, but we're not really. This is not really the physics of it. This is not really. We're not really in Bridget dynamics right now, so it's not necessary to express it as such. But it's important for us to make this important distinction. So think of this as our Noether's theorem. So we have some mapping, and then it equates to some other symmetry, which doesn't change. So no matter what you do to a certain person here, or no matter where you move a person, or do whatever the heck you want to a person, it is theorized, or it is best said that their wave function, or at least the probability amplitude for their for whatever the heck we're measuring from them. Let's see, the orientation does not change. So that is our symmetry, and so our probability amplitude, or our mapping or assigning of values, equates to, of course, symmetry. So there's our application of Noether's theorem. Noether's theorem is very important in physics, but it's a really good thing to apply here. So now the thing is, the wave function is not always discrete, but mu bar is always discrete. So what if we made mu bar into a continuous function? So now, what we think of it as let's think of, there are many ways of representing mu bar, of course. You know, so the measure, or every person or every femboy can have a different probability amplitude, just like how every elementary particle can have a different wave function, or norm of the wave function itself, or yeah, just wave function. So I suppose let's dig into some examples of mu bars. So one example of a mu bar, which is a great example, is trigonometric functions. So a wave like mu bar. So actually is sometimes explicitly defined that psi, which is a wave function, is e to the ikx, in which e to the ikx is cosine kx plus I sine kx. This is precisely the cis function of kx. It's explicit stated, and you can see, oh, it's cosine sine, it makes wave, hence wave function. Haha, nice. It's very neat reference. But it's actually a good model for, say, gender fluid people. So so we have our mu bar. So now we have a probability amplitude. Okay, let's say remove the I and just say e to the x, or rather, let's take the square of the minus, or the minus of the square of x. So let's say mu bar is now e to the minus x squared. Now we get ourselves a Gaussian distribution. You notice that summing all the values from minus infinity to positive infinity gives us 1. Because as the limit, notice that the limit as x approaches either plus minus infinity of e to the minus x squared is always 0. You can check that for yourself, but notice that as you travel along the graph, it just eventually goes off to 0. This versus our mu bar, or mu bar, and then this is of course or the axis for the mu bar. This is our axis for the O. Now, yeah, because again, we're only, of course, yeah, we want to regard those who aren't. So, now you may be asking me, what about the mu bar of straight femboys? Well, of course, since the mu bar is only strictly talking about the measure of homosexual tendency, then really the mu bar for any straight femboys or femboys beyond 0, or having an O component of beyond 0, is pretty much a 0. So you'll notice that an actual Gaussian distribution here is pretty discontinuous, because once we get to 0, it should jump. Once we get to 0 or no sexuality, basically. They don't like anyone. It should jump to 0. So what we want to actually write here. There. So this is the function. But from here on out, it's pretty much smooth stuff, and then it's all 0. So you notice that the graph itself is thicker than the regular thing. So I'll use arrowheads to where the graph is headed. So this is in reality what the graph of our mu bar is, because as we explicitly defined a while ago, because of course any straight person has no inherent sexual tendency. However, those who are actually closer, or those who have a viewpoint that are closer to the origin or closer to being asexual, are actually have actually less tendencies for males and maybe more tendencies to females. Some of you may be asking me, how about bisexual females? How about those who like both who like both girls and boys, or males and females? Well, we want to reserve them for a different kind of interval. Wherein zero is not defined as asexuality, but rather having both. So here we're working with a zero. We're practically working with the group Z, and plus here. So our additive inverse is zero now. However, because we don't want them to be non-zero, so we want them to be given a choice, right? So when we want to speak or talk about bisexual people, of course, we're going to be working with, actually, not just Z, because one half is not part of Z. We're working with R. This is still a group, by the way. Yeah, because Z is a subset of R. But if we want to talk about bisexual people, though, we want to work with R and the multiplication. So R equipped with multiplication. I want to write structures in terms of angle brackets. I know that in differential geometry, this is the notation for a scalar multiplication, but scalar multiplication is really just dot products. So it doesn't matter. So I'll really just use angle brackets for this. It doesn't matter. So if you want to talk about bisexual people, they really belong in this commutative monoid. While if we're talking about gay people and straight people, so it's strictly just those two and asexual people this time. So this time our identity element, so E is 1. While here our identity element is 0, because our identity element, if you recall, of course, from previous lectures, that whenever we compose an element with its inverse under this operation, under this binary operation or n-ary operation, and you do that, we should get okay. So consider this a binary operation first. So you could interpret this as an n-ary operation, but it'd be best right now to say that it's a binary one. So it takes two outputs from R and gives us another value in R. And then likewise for this plus operation, it's also a binary operation. Okay. If you recall, of course, when we compose any element in R with its inverse under this binary map, we are supposed to get this. So of course, since it's multiplication, as you know it, 1 times 1 is 1, of course, 2 times 1 is 2, 2 times 4 is 8, you know it, repeating multiplication, that kind of stuff. You notice that each inverse or each reciprocal, each inverse or multiplicative inverse of any number in R is their reciprocal. So the multiplicative inverse of 1/2 is 2 over 1, or just 2, because notice that when we do multiply them, 1/2 times 2 is just 2 over 2, which is 1. It gives us this. So yeah. And the reason why it's commutative because we can switch the elements over. So yeah. So actually, so it's really just O this time. So actually, instead of R, we're talking in terms of O here. But every component is described as some element in R. We can think of O as R itself, but there are many ways to interpret O. So O maps onto O, step O. every femboy here has a multiplicative inverse, an opposite, an exact opposite. So if you in fact exist inside this abstract space, which is not real, we all don't really have doppelgangers in real life who. Okay, let's suppose that I'm straight, right? There's no such thing in real life as a doppelganger that is that's gay. I don't have a gay doppelganger. So let's just for example, okay. Wait, hold on a second. Okay, I was called to do something. Okay, if I'm not gonna get sidetracked any further, this is another perfect reason why mathematics is merely just a model of real life, and that this is an intrinsic of real life here. This is another example why you shouldn't apply this in real life, or use it to dictate other people's relationships. Because, as I said, I don't really have. Suppose that I'm a straight person. I don't have a gay doppelganger out there, right? I don't have an identical person who is more, maybe, and likewise for the appearance interval, for P, there are two versions of P that we want to think of. P in terms of addition here, wherein this time they are androgynous in nature, right? Well, both P's, both zeros or both origins or both identity elements in P are actually androgyny, being androgynous. Really, if you're making a mix of both genders, or actually no gender at all, so really non-conforming to any gender at all, non-binary, then I guess this sort of principle somewhat applies. And likewise with gender identity, we have two types of spaces here. For G, I suppose, which we will call the interval for gender identity, we will have two types. Where in 0, the one wherein its identity element is 0 is basically it being a gender, and then the one wherein it is its identity is 1 is it's bigender. Okay, bigender. But going back to our lesson here, of course we have two different types. Here now, well, it makes sense for their mu bar or definition of mu bar that this is what it should look like, according to our previous definition. And that would be for this space here, for this structure. So if we apply this map on the structure, this is what we get, according to our previous definition of mu bar, wherein no straight person is, at all. And this map doesn't exist, although its limit exists. Ultimately, that point is nowhere on the image of this map. Now, what would that graph look like here? So suppose we construct a mu bar for this space. Its mu bar is pretty much the same. This time, this part here is shaded. And then that just goes off to 0 at infinity. Okay. So the difference between here is that, of course, our input here is 1. This is 1, and then our input here should be 0. So actually, this one here is the one that's shaded. So here's a good thing. This is a good example of why one mu bar is never enough. Or when we construct a mu bar for a certain space, right, or a certain type of femboy space, we need to be wary about what we're constructing, because it could be that for a different type of operation. So okay, suppose for now that we compose these two structures together, like a ring, which is R plus, and then this is a ring, but suppose that we construct O to be a ring. Now, what would be our mu bar now, given this map, of course, this Gaussian distribution? Well, I suppose it would be both, because we have to consider both under both, or it would be two separate spaces this time. we split it into two separate spaces and then have these two, because we cannot have a function wherein at one input or at one point there are two inputs. You notice that if we shade this, we have two inputs here or two outputs for this one input, and you know that would make it not a function. I mean, yes, I understand there are certain functions that have two inputs like this. This graph over here has two inputs at this interval, but well, it's not our concern for now. We're talking about bijective functions here. This over here, that wouldn't have an inverse, or I believe that's only a surjection. We're talking about bijection here. When we're talking about mu bar is bijective. That's what we want to say. Mu bar is bijective. Now you may be thinking, oh well, it's still sort of part of the function. How come it's still bijective? Because that's the reason why we hold this part here. This input, this output here is, or this point here, or this point in mu bar, or the mu bar axis is not part of the output, or not part of the image, but rather this one is. Well, of course for this structure, but for this structure, this time it's 1 here. So I'm gonna list this. I'm gonna write it down. 1. Okay. So how about sine? Sine is basically just this, but we restrict it. Sine can be thought of as a Gaussian curve, and that's actually the reason why how the result, the Gaussian integral is equal to pi over 2. So one reason why you notice that, well, it looks oddly like a sine x over x curve, right? The sine x over x curve looks like this. And then these two, as sine x over x goes off into infinity, it disappears, or it vanishes to 0. So this is like an oscillating moment that's going down and down and down. You'll notice that this is also a solution to the harmonic oscillator, but that's not what we want to talk about here. Now, how about this one? You notice that the Gaussian function here, this, if you restrict it and make it just this, and then multiply it by some value that makes, or rather, if we want to take the sine of absolute value of x, or just take the absolute value of the entire function, we would get something that this graph is shifted upwards, or there's no values are, and if we restrict it again, we would get something that looks akin, or something that's close to a Gaussian curve. And that's a neat, that's one of the stepping stones in proving that the integral from minus infinity to plus infinity of e to the minus x squared dx, is equal to square root of pi. Convert it to polar and then do some other stuff to get the result. It's a very neat proof. And that's another reason why trig functions, especially the sine x over x function, is an interesting thing. Is an interesting form of mu bar. So let's say now that mu bar is equal to sine O. Okay. So so this would be our function here, our O. Then this is our mu bar. So here, of course, you remember the limit from elementary calculus that as theta or as O approaches 0, this would become 1 according to a sandwich proof. So yeah, it's a very fascinating way of modeling it. So you'll notice now that this is our probability amplitude, and this is actually a good way of describing probabilities of it, because you notice that the integral from minus infinity to plus infinity of this one is in fact 0. If we take areas of every snippet of this if we take areas under this curve all the way to from minus infinity to positive infinity, we'll notice that it vanishes to 0. So the integral from minus infinity to positive infinity of mu bar in this case, so dO of mu bar is 0, and that's another reason why it's good. Or it would actually be 1, I believe, because we reach all the way here, so we restrict it. We believe that this is 1 over here, right? This output here is 1, and then all these other values cancel each other out, because this doesn't have an equivalent amplitude that such that when we add it, it doesn't really so actually this is 1. That's pretty neat, and this is why this is a good wave function. It's a really good one. Aside the Gaussian one. The Gaussian one is also a good one. And okay, I'll just write here. Sin O is 1. So let's list down some good mu bars. I'll leave it to you guys as an exercise to prove that these limits can converge to 1. So sine and also E. Oh, and you'll notice that this is actually equal to square root of pi. Not 1, but the square root of pi. However, you can normalize this. This is actually not good. So what we want, this is not good because we want the probability to sum up to 1. That's square root of pi. So, okay, so let's do this quickly here. What we want to do is normalize the function. So really, what we want, what the real mu bar that's good here, is not e to the minus x squared, but the pi, or actually 1 over the square root of pi, e to the minus x squared is equal to 1. Because notice that, so the integral of minus infinity to plus infinity dO of 1 over the square root of pi e to the minus x that's O squared e to the minus O squared. Now we can take this 1 over square root of pi out because it's a constant. So this gives us 1 over the square root of pi, integral from minus infinity to positive infinity with respect to O of e to the minus O squared, which is of course 1 over square root of pi times the square root of pi, which gives us, or vanishes off to 1. And this is why 1 over the square root of pi of e to the minus O squared is a good function to describe the mu bar. So let's give a summarized list of it. Good wave functions. Let's say some, because this is not all of them. I'll leave it to you guys as an exercise to find other good forms of mu bar. So mu bar of O is equal to 1 over the square root of pi times exp of O squared. So this 1, 2 is mu bar O is equal to the sine sorry I didn't say this a while ago. I didn't say the one over the square root part. Square root of pi part. I do have a feeling that this sign here is not really not nice, or there's something here, it's not normalized. I have a feeling it's not normalized. Actually, we have a good reason to think it's normalized because we know the area, right? Minus plus infinity, the O would be our area, and then so that one big amplitude, which is 1, and then some pi, I think pi, that would really just give us 1, and then the others, since they have their own amplitudes that are the opposite, additive inverses, they all vanish to 0 anyway. But then again, that's all with the limits. So I'll leave it up to you guys as an exercise to prove that the limit converges. So I believe that's all we want to discuss for mu bar. I'm sorry this lecture was longer than intended. I wanted to incorporate some calculus into this. And so yeah, don't forget the exercises. So I already proved that this is a good form of mu bar because it's when we take its integral from minus infinity to plus infinity, we get something that's 1. Now I want you guys to prove that this is a good form of mu bar. I want you guys to show that the limit does converge. And if the limit does not converge, I want you guys to normalize this function such that its integral does converge to 1. So that's a good place to start.